Good afternoon, everyone. Sorry for those teething problems. It's yet another system to share, to share presentations. So basically, myself, Brennan, and Thomas will be going through AI-driven battery thermal propagation prediction. So maybe go to the next slide. Or no, I can do that. Okay, so yeah, we'll go through a little bit about AVL for those that don't know us, and then get into the meat of the presentation to discuss our expertise and background and knowledge and processes in this area, and then of course onto the Q&A. Okay, a little bit about AVL. So for those that don't know us, we are one of the world's leading mobility technology companies, involved heavily in the development, simulation, and testing in the automotive industry, also battery energy storage, off-highway, agricultural, rail, a wide range of mobile and stationary applications. We are involved in quite a wide range of different programs, from early research and development all the way through to concepts and production programs. Really our focus is aligned with the urgent need globally for a greener, safer, better world in mobility. Whoops, sorry, let's go back. Yeah, so a bit more about AVL. We were founded in 1948, just after World War II, with Marshall funds coming from that. We're a privately owned company, owned by the List family, headquartered in Glatz, Austria. You can see we're truly very much a global company, got tech centers all around the world, where you'd expect an engineering company to have tech centers. About 12,000 people. Also, heavily biased towards scientists, PhDs, and engineers. We reinvest a lot of our turnover into R&D and focus heavily on patents and developing new technologies that we patent. Okay. Brennan, would you mind doing the next slide? It seems to be such a long lag here for me.
No problem.
There you go. Thank you. So yeah, just to talk through kind of the three areas. So we've got three divisions, if you like, within AVL: the engineering, simulation tools and solutions, and the testing solutions. So myself and Thomas and Brennan represent those three different areas. So the engineering projects, we act as an extension to our customers and conduct all sorts of engineering programs, like I discussed a little bit earlier, but really anything in the mobility and stationary energy space. Simulation solutions, we sell. Our software is commercially available. The software is developed over many years of working on customer programs. We have software that we've tailored specifically for the problems that the industry faces, to address the problems that the industry faces. Also similar with testing solutions. We sell test equipment all the way from conventional engine dynamometers and test equipment, instrumentation, data acquisition and control systems, all the way through to battery energy storage, cyclers, emulators, and test cell controls. So we'll go into those three areas in a bit more detail here. Next slide, Brennan. Okay. Great. The presentation is comprised of going through the combined approach of simulation and testing that I'll take you through, and then getting a bit more into how we validate the models, and then advanced methods and data analytics, and also demonstration of a no flame out design. And again, this is really focusing on the three pillars of the engineering division, simulation tools and processes, and also the test methods and equipment, all leading towards a no flame out battery design. Next slide. And again. So first of all, I'll go through the summary here of kind of the factors that we look at. So maybe just page down one more time. You can see when we consider thermal propagation, we consider, of course, the cell level attributes as well as the pack system level attributes. So quite a few different effects that need to be considered and simulated and tested. We rely on a combined simulation and test methodology. Simulation models are quite accurate at this point and represent the physics very well. But there's also physics that is, somewhat stochastic and less predictable that we need to capture in the test data. So really, we rely on a combination of test and simulation. Next slide. So talking a bit more about the process, the engineering process here. So when we characterize a cell runaway behavior, we're trying to characterize the behavior shown on the left-hand graph here. So in terms of the heat release versus time, the stages of heat release before and after the vent opens. And really, that whole characteristic, including the gas flow, the particle flow, and so on. So the middle column here shows a typical cell characterization test that we conduct in an inert gas. And the typical quantities that we measure are, again, the heat release, so thermocoupled battery cell, as well as thermocouples around the chamber. So the gas temperature released, the gas pressure, the volume of the gas from the cell, and also the composition or species of the gases from the cell. We also analyze the particles, so that the particle trace with high-speed cameras, and the composition, so material analysis of the particles coming out of the cell. And then typically these tests are completed multiple times to try and get an assessment of the variation from cell to cell. And then, of course, we have multiple methods of triggering the cell, depending on what we're trying to achieve. Most predominantly, we use a heater pad to trigger, though. And then, so the right-hand column really shows the simulation world equivalent of what I just went through. So we mimic that test in a simulation environment, and then use the comparison with test to correlate the simulation model. We've got a significant database of prior tests and prior simulations, so have pretty good confidence on how a cell is going to perform based on the design of the cell and the chemistry. But of course, as I'm sure many people on the call realize, a relatively small change in the cell composition design can have a significant effect on the results. So we prefer to always use this approach of characterizing the cell in test and then tuning the model. Okay, next slide. And then taking that further to look at some of the other attributes, particle characterization. So as I mentioned, we conduct optical measurements during the runaway event in the chamber to understand the flow of particles. We analyze the particle size and composition after the test. We also conduct our abrasion testing, so understanding the abrasivity of the particles against other materials or components in the pack, and use that to correlate abrasion predictions in the model. And then we've got the arcing characterization portion, So using arc tests with various gases, various electrode designs and electrode spacing and so on, to characterize the model behavior. And finally, on the right-hand side, showing the flammability. So of course, we've got decades of experience in combustion prediction in internal combustion engines. So it's really taking that methodology of understanding the likelihood of flammability based on the stoichiometric ratio, the ratio of fuel to oxidizer, to really understand the likelihood of a ignition of the gases. Okay, next slide. And then, yeah, pulling all of this together, really, this shows one example of correlation activity between test and simulation. So the column on the left shows all of the main inputs at a cell and a cell stack level in this case. I won't go through them all in detail, but the graph on the bottom is perhaps more important. It's showing the comparison of the predicted cell heat release in red to the measured cell heat release in gray, and essentially, yeah, a good correlation, good comparison there between the two. And then in the middle, the main graph here, we have the time to propagate between cells. So we kind of have a zigzag curve of low propagation time and then followed by a higher propagation time as we go across a thermal barrier, and then a quicker time between two adjacent cells, for example, between cell 2 and 3, and so on. You can see the correlation is very good here until we get to the last cells, and we show in this study, the graph below, the stochastics in the thermal runaway behavior really begin to kick in here as we get further through the cell propagation. So the variability essentially in the test results, it can be seen, and we don't have that same variation in the simulation. So ultimately, we use this simulation to evaluate all sorts of different phenomena in the pack, the cell trigger, impact of the cell trigger characteristic, evaluating convective and conductive heat paths, the gas effects, and so on. So this tool can then be exercised to optimize the pack design, minimize or maximize the time to propagate or eliminate propagation, and so on. For some reason the movies are not playing here, but yeah. Oh, there it goes. So yeah, basically just showing here the visual representation of cell-to-cell propagation. Okay, next slide. So yeah, this shows, I think, when it all comes together and we optimize the module, cell and module and pack designs, we're able to achieve a no flame out design. Essentially, no flames come out of the pack when it's deliberately initiated on one cell. And the external temperature of the gases outside of the vent stay below 100 degrees C. So I think quite impressive, really, when you consider the energy inside the pack. Quite a few design considerations need to be made here to achieve this. This particular example is with an NMC 811 pouch cell. So obviously one of the harder cells to control in thermal propagation. So consideration of the cell design, including the pouch foil folding design, and its vent, trying to guide the vent path from the cell through the module and through the bottom structure of the pack. So the other features in the module and the pack are really about guiding that vent gas, allowing expansion of the vent gas to cool it down, having appropriate structure and particle traps in the in the design to enable particles to drop out of the air and prevent further initiation sites. The little graph you can just about see there shows three temperatures. The highest temperature is on the module that was initiated. The middle temperature there is a temperature on a neighboring module, and then we've got the cooler green temperature, which is outside of the vent, outside of the pack. So you can see a dramatic reduction in temperature from 800 degrees C all the way down to sub 100 with this design. Okay, next slide. All right, Thomas.
Yep, I'll try to take over here. So let's see if it works for me. Otherwise, I also will simply ask Brennan maybe to advance the slides, but I will give it a shot. And yeah, I think it works. And yeah, I will explain a bit how the AI driven comes into this entire equation and why we state this at the moment, and explain a bit in more detail the simulation technology behind the process that Ben just laid out. Let's see if it advances. Yeah, I think I also struggle to advance the slide. So if I may ask you, yeah.
I can go. I can do it. It looks like it was not working.
Yeah, no problem. Yeah, so at the core of the simulation technology, we are using 3D multiphysics computational fluid dynamics, so CFD, to describe the thermal runaway phenomena such as the venting gas flow, highly turbulence, flammability, as Ben mentioned. You see a bit of an image here on the left side of a module that's has a melted portion and also hot venting gas coming out to a lesser degree. And here comes a bit the connection to manufacturability. We also simulate or use SPH code, so smoothed particle hydrodynamics, to simulate the injection of thermal barriers, potting foams, or any adhesives that might be crucial. But truly, these are the more detailed simulations, so to say, and typically they take some days, hours, if sometimes weeks for a very large pack in very high detail. So it really gives us kind of like the most maximal detail possible. And so we need for a realistic, also from a time perspective, realistic development process, we need faster techniques as well. And here we switch over to system simulation that we see here in the middle, where we model more like a block diagram style approach, modeling the interaction between dedicated components. So typically this could be the battery in the larger context of an application or vehicle, but also we use it to model much coarser 3D CFD of a modular pack. So you see here in the image a discretized thermal propagation of a module with a few cells. And this runs more on the time schedule of real time, so or within minutes for typically a problem. So much faster, runs also on much cheaper hardware, and this is much more accessible. And but even that is basically not enough speed to really develop a compelling or screen the entire design space. So we go one step further and use the simulation results from the system simulation, where it runs fast enough that we can get a lot of data to train and develop machine learning and AI tools. So this we see on the right. And once these methods are trained, we can evaluate parameter combination and different design variations within seconds and invest trade-off basically in real life time. So changing a design with the slider, you get the results immediately, basically. And this opens also the door to optimization of entire layouts, evaluate design change evaluations. So in the engineering approach, basically, we work our way from the right side back to the left side, starting with the AI models, find the most suitable design that's also safe, then tested in system simulation in more detail. And as the design develops and a CAD becomes available, more cell testing becomes available, we go back to 3D multiphysics CFD and try to simulate it in as much as detail. So at the final real physical test, we hopefully don't get any surprises. And yeah, this method has worked very well for us. If you may advance to the next slide. Yeah, to give you some impressions of the multiphysics 3D CFD, at the foundation, we need to cover the normal operation, let's say, or the basic effects, such as conventional heat transfer, on the heat generation of the cell under normal operation, but also all relevant materials in the module and pack, such as insulation materials, bus bars, any housings, heat transfer to the environment. And that's really the cooling system. That's really the basic. And on top of it, we put our hazardous effects. If we go to the next slide, we should see in a bit more detail what we are doing here. So as Ben mentioned, the basic information needed for such a simulation is the cell information. And here comes the connection to manufacturability. And ideally, we are very reliable and very with very fine tolerance manufactured cells that are mostly as equal as possible. So one measurement can really cover the effects, but we need the heat release that we describe the venting behavior of the cell in the model. We would cover melting by mainly the material parameters of the materials involved. We need to consider burst disk, both the location, but also the behavior of the opening of the burst disk, for example. And then we would simulate also the flammability. I think if there are a few animations, if we move on for one slide, and while this you will get a few impressions here. We do also cover advanced effects, or what we say, these are more really more sophisticated, and this especially involves the particle ejection that Ben mentioned earlier, arcing risk, or we would also pair such a simulation with additional crash simulations, for example, deformation of the back, and venting gas flows might change, and evaluate such scenarios. So here you see on the animation a quick depiction of typical simulation results of such a high fidelity simulation. And this gives our engineers really a good confidence and guidance if their design in the end works well. If we move to the next slide. And I just see that I stay a bit in time. So with one more animation, we have basically three variants of how we can cover the heat release. So the most straightforward and also most reliable version up to date is to do a measurement fit based on measurement data of a single cell or a few cells in a mini module, so to say. And we would use the direct output of that measurement directly in our software with some conversion tools. However, it's becoming more and more a topic also to use these types of simulations earlier, before you know exactly how the cell would behave. And here a solid body chemistry approach comes into play, where we say, okay, different types of the cell or portions of the cell we can describe with different representative species. And then we basically, in the simulation, burn this representative species with a dedicated reaction mechanism. And this allows a bit more a predictive approach, and it works quite well, also proven from literature for different chemistries. If this is also is not even sufficient, or it's something more is required from a cell technology, for example, something really novel on the market, and we cannot describe it yet with the existing models. We can also use an empirical model on top of it, or user-coded model, so to say, that can be freely populated. Such depicted here as a smart formula, where the smart part is that the user does not need to take care of the coding part per se and how to connect this to the CFD solver, but really can focus on the empirical equation at hand. Yeah, with the cell heat release out of the way, if we move on. We can then focus really more on the advanced effects, and as the test that Ben mentioned, we use to characterize arcing particle ejection. For example, as you see here in the middle, particles coming out, hitting a barrier and melting it much faster, for example, than just the pure hot gas by itself. So we really saw that we need to include this in the higher fidelity simulations to get really accurate results, as it can make the difference between a no flame design or a design that's more conventional, let's say it like this. And we do combine these capabilities also in the simulation, that the actual venting gas behavior and the hot particles interacting with it can increase the flammability of the gas, but also can lead to higher arcing risk across the module. Yeah, as I do say, more advanced topics, but I think definitely worth looking into them. And with the main challenge on the next slide, I think we see a bit of a way how we bring this into system simulation. So we really need to get from a 3D CFD on the left side, something really complex, a lot of computational cells, do something more that we see here on the right side, something more abstract, where we really model the crucial parameters and parts of the models with individual blocks. So, for example, you see some blue blocks here that represent the gas volume, or you will also see some gray blocks representing the housing, and you will have blocks modeling the battery modules and chemistry itself in such a system model. And this runs much faster. So we are able on the next slide to really put this into a workflow to train AI. And you see it here at the bottom a bit, the earlier described workflow already, also a bit more of an impression how complex these models can get on the system side, but it's very worthwhile producing such a model because it allows us to achieve our objective of simulating a battery pack thermal propagation within a couple of seconds instead of days or hours before, and allows us really to find an optimum combination of thermal propagation relevant battery parameters. And on the next slide, actually, we see a bit of an example in more detail of such a system model. But if we move on even further, we do see an example use case. And here you see, for example, the level of discretization of a module that we would typically use in such a simulation. But ultimately, we want to get to an AI machine learning model that we now can use to, for example, vary different parameters such as the compression bed material, the thickness, the venting device numbers, and really investigate the trade-offs for respective outputs that might be relevant. So, for example, we could look at the trade-off study here, combustion probability at a certain location versus cost of the design. And for example, this 450,000 configurations with the trained machine learning model, you're able to evaluate in 8 minutes. So you can screen really the entire design space and find the 2-3 best candidates for your design. And obviously, in a more complex production setting, this would be an even more widespan study here. For this example here, I think if we move on, the final result was then to use a specific thickness on the sheet here and specific venting flow devices. But this is the design guidance basically you get out of such a trade-off study. And to make this really accessible, and here kind of like comes the buzzword AI a bit into play. We package these machine learning models then into a compelling tool where you really have a nice GUI and can operate this. Even a novice simulation engineer can operate such a tool fairly quickly and get quick results out of this. And I think on the next slide we will see a quick impression of the actual packaged or finished product, the finished tool. And all the machine learning models are actually interchangeable, so they can be updated as more data comes in. This can be highly customized to the respective use case of the respective industry. So it's a really quite a nice approach. But yeah, to finish this off, the models obviously are only as valid as the test data they based on are. And I think here I would like to hand over to Brennan actually to explain us a bit in more detail how we can gather really highly validated test data also.
Thanks, Thomas. Yeah, I think in the interest of time here, I'll try to be efficient. And I think my colleagues here did a great job doing an overview of what it takes to get to a truly safe design by leveraging AI in a lot of the workflows here. And so as a critical part of those improved workflows using AI, and we're starting, AVL has a slew of tools that are starting to implement machine learning and AI themselves, a lot of which were highlighted in Thomas's section. I'm going to sort of tie things together to, share the idea of, how can this be translated and handed over to a customer's hands to have the power put into their hands to be able to do a similar type of development to increase the safety and the speed to developing, improving the speed and the cost to being able to develop such a design. So on multiple fronts, here's the stuff that can be implemented in your workflows physically. And the first thing I want to debut here is the safety test chamber from AVL. So the data has to play several critical roles, especially when you're trying to leverage AI. Data becomes the most important thing, the volumes of data, but importantly, the quality of data. And on two ends of the workflow, right? You've got the training data, you've got to get a lot of experiments done. I mean, we're looking at a lot of different parameters and angles that both Ben and Thomas were highlighting. I mean, you're looking at the different failure modes, you're looking at the different pathways of propagation coming from the cell level, perhaps the mini module. But then on the other side of the experimentation, you're running your simulations, you're using AI, and you're trusting a lot of what the AI is generating for you in terms of the design, and you're looking for correlations, but you have to go back and validate that with more test data. So a lot of test data is still required for this type of work. And so this is the safety and abuse testing side of things. So that's why it's the first thing I'm covering. This is basically the value added here is being able to bring what often is done off in a desert hundreds of miles away to avoid, safety regulations and entities, perhaps physical operational safety, lower costs, things like that. But the trade-offs there is that your data is proximity-wise pushed really far away. You have less control over the actual data, which again, the quality of that data is paramount for having these AI models improve things in the design front. But also you are able to use something like this to abide by all the standard industry standards, which the compliance matrix is here highlighted. So you've got the standard UN, IEC, ISO, SAE. And the cool thing about this safety test chamber is that now on site you can support underneath. You can have your vibe table, and so your vibration mechanism is already included in this. Again, compliant with UN 38.3 and everything else. You have your abuse mechanisms ranging from nail penetration to crush to altitude, thermal testing, which Ben talked a lot about, which was implemented for the no flame out design. And then electrical abuse tests. So you've got the external short circuit, overcharge. You can even do internal short circuit. And so this brings everything home to be able to run high fidelity, highly controlled test environment for the user, for the battery developer, and also being able to accomplish that in a high throughput fashion, since a lot of tests are going to need to be done and a lot of things need to be measured. Something people don't think a lot about as far as the safety side of things is the age of the battery. So this is our BCTS, which we debuted as a company last year. And there's been a lot of interest around a fully integrated ecosystem for getting a cell to be tested, degraded, and then ultimately can even be abused with really precise control, really accurate measurements. Also has, you can see the gas sampling unit is integrated there. So when certain thresholds of gas constituents are detected within the chamber, then certain countermeasures can be implemented to immediately stop the test or proceed on to a different step of the test. You've got the cyclers and the power sources, everything contained in this cabinet with the cables completely integrated into the environmental conditioning system. This, like I said, can also control the safety test chamber, which I covered on the previous slide. And it all comes together with the test automation, which is Lynx here. Lynx is sort of a lot of the battery test engineers on the call might be familiar with battery test software that you're using to control your samples. You know, you might have dozens or you might have hundreds or even thousands of cells on test at any given moment. Lynx is sort of the Swiss Army knife of battery test automation. So it allows you to completely schedule, control, automate all of your tests to make the most efficient workflows and lab setting as possible. And this includes the safety and abuse testing program for your cell and your mini modules. So I'm hurrying along here a little bit because I think we're right at time. So yeah, I wanted to importantly highlight data analytics, which is a software suite by AVL, and it is a lot what it sounds like. It's a package that it's a data analytics package where you have a bunch of customized data visualizations that can be tailored to specific thresholds, metrics, signals that you're trying to flag, either statistical outliers or meaningful physical metrics that you want to flag when something's starting to happen in the cells on test. You're going to be able to identify that right away. And then all of these statistics can also be aggregated through this platform and extended beyond just the test field and actually out into the actual field, the product field. So this is cross environment. It's everything from the lab bench all the way out into when you really want to start improving your AI models, for example, it's critical to capture that field data and reincorporate that back into your design and test flows into the lab to do the side-by-side comparison. So it's essentially the sky's the limit in terms of how rich you want the data set to be, but now you've got the well-controlled lab setting data comparing to what the field data is producing for you. So it's always a continuous improvement sort of idea here. This is sort of a bit of a summary slide. Our customers now have the ability to take the hands-on equipment, incorporate that with the AI, that TR and propagation prediction instruments that they're developing and models that they're developing, and scale a lab to the appropriate scale to be able to capture all the critical, safety critical parameters that are going into their design to ultimately output something that's going to be a useful product at multiple scales. And this not only applies to the pack development, but this isn't just an idea that's living off in a concept or the company portal somewhere. The BCTS, that's the battery cell test system that's fully integrated. These have been deployed with our customer partner, Volkswagen Power Co., which a lot of you might have heard of before, out in Salzgitter. And so their labs have been fully outfitted with these integrated systems at scale to be able to support their battery production at scale. So they trust these for their own workflows. And so I think we're a couple minutes over time here. So sorry if I blew past my section a bit quickly, but would love to, if there's time for some questions, would love to field those now.